Here's an introduction to galaxy mergers to accompany Chapter 28 of the textbook Astronomy from Open Stax. So first, when we talk about mergers, there's sort of two classifications that we put these into. So we have major and minor mergers, and they're exactly what you think they would be. So major mergers are when you have two galaxies that are about the same size, or at least comparable in size, and they collide. And this is obviously an extremely disruptive event to the structure of both galaxies, and what's left behind is probably something elliptical, and it likely looks not much like either of the two galaxies that collided. Then on the other hand, we have minor mergers. This is just a artist depiction here of what we believe is happening in the Milky Way. So we have the Virgo stellar stream here, and in this case you have much smaller galaxies being absorbed by much larger galaxies. So we're talking about like mass ratios of like 10 to 1 and stuff like that. And in that case, the bigger galaxy can absorb the smaller one. It'll change the structure of the bigger galaxy, but not in a very dramatic fashion as you have with a major merger. So let's look at some evidence that mergers happen, just looking at our own Milky Way. And in this case, let's consider minor mergers. So what we can do is we can look at the properties of stars in our galaxy and then infer that some minor mergers have happened in the past. That's one approach. So what we're looking at on the left panel here is basically a plot of velocity components for stars in the Milky Way. It doesn't matter that you understand really the details of this, but you're basically looking at the velocity in kind of a rotational sort of coordinate in the galaxy, and this is the other directions combined. And then on the right, you're looking at the velocity in the rotational direction versus the radial direction. And what you can see, this is just the stars that we observe. There's the stars that are grouped together that are similar in composition and in age, and they're colored blue. There's another class of stars in our halo that are similar in composition and in age. They're in red. And then you have the thick disk in this region here. And you can see that the older, more metal-poor stars, they are in generally a kind of distinct region from the red. They overlap, but many of the blue are out on their own. Then on the bottom, what you're looking at are the results of a simulation that assume several billion years ago there was a small to maybe medium-sized galaxy that merged with our own Milky Way, and what would you get as a result? And in this simulation, the gray is again the thick disk. The red, these are the stars that were a part of the original, sort of proto-Milky Way. And the blue, these are the ones that are a part of the smaller galaxy that merged with our Milky Way. And you can see that you get a very similar structure in the simulation as you get to the data. So that's one piece of evidence. You can take these simulations a little bit further and compare to observations. So what we're looking at on the right here is a plot of we call it the metal content. It's basically everything heavier than hydrogen or heavier than helium. You have the metal content versus the time, or the age of the star rather. And the blue, this is again a grouping of stars that we observe in our halo. So they tend to be older and more metal poor. And then the red, this is a distinct grouping that have more metals and can extend, and you can have sort of younger stars in this classification. You take a look at the same simulation we talked about on the left, where you've merged this one galaxy with the Milky Way, and you expect this pattern here. So the proto-Milky Way, these are the more metal-rich stars. The one that we merged with, these are the more metal-poor stars, and qualitatively at least there's quite a bit of agreement. So that's one piece of evidence that we've had minor mergers in the past. There's also, the Virgo stellar stream that I just talked about on the previous slide. That's another piece of evidence. You basically have a literal streak of stars sort of through the sky of similar composition. If you want local evidence for a major merger, we're obviously, one hasn't happened yet that would completely destroy the Milky Way as we know it, but one is going to happen, and we can look at galactic velocities in the local group. We talked a little bit about this in the Milky Way formation lecture. So the local group, this is the set of galaxies that are near the Milky Way. This is kind of our local little minor galaxy cluster. It's mainly characterized by three big spirals. So you have the Milky Way, Triangulum, and Andromeda. And we can look at the relative velocity, and the Milky Way and Andromeda are approaching each other at something like 300 kilometers per second. And so you can take a look at a visualization of what this is going to look like. Is we just here have our Milky Way, and then this movie is going to zoom out in a moment. And so we have our Milky Way there hanging out. Andromeda and Triangulum are kind of approaching us, but it's a really more direct path for Andromeda and the Milky Way. They're kind of coming straight at each other. And so the Andromeda galaxy is going to approach, and as you can see, the two galaxies are now interacting strongly gravitationally. There's the first pass. You have the greatest separation between them, maximum separation, and then they're going to come back together again and merge. And the reason they kind of swirl around each other is the same reason water swirls around in a toilet bowl, right? It's just there's a gravitational potential well, and things are going to, when they coalesce, are going to follow kind of a merging pattern. And of course, they're not going to just directly collide. They're going to be able to slingshot past each other and then spiral inwards from that gravitational interaction. So that's going to happen in the future, and we can tell that from the relative galactic velocities. There's, of course, lots of other circumstantial evidence for mergers. You can look at structures like this out in the universe. This galaxy is obviously not really a gravitationally stable object. It's not spherical or disk-like, so probably can't stay that way. And it looks pretty obvious here that what had happened is two galaxies collided and were ripped apart, and they're in the process of merging into one. And there's plenty of examples of this if you look out in space. In terms of the galaxy merger rate, we can take a look at, this is the rate of mergers per galaxy. This is a log scale versus time. So what we're looking at here is the redshift, and you remember from the redshift lecture that the larger redshift is further away in distance, but it's also further back in time. And you can see that the rate of major mergers per galaxy is decreasing substantially. So there's something like a few percent of galaxies are undergoing major mergers in our sort of modern universe. If you consider all mergers, major plus minor, then things are continuing pretty steadily. They haven't changed that much. There's a lot of little tiny galaxies out there that are being absorbed kind of all the time. And if you look out in the universe, it's maybe not surprising that you see that elliptical galaxies tend to have more nearby galaxies than spirals. So that kind of adds to this. That's a piece of evidence for ellipticals being formed by bottom-up formation. Right? The elliptical galaxies are nearby other galaxies because there were probably even more there in the past, and some of them merged to form your elliptical. In terms of the time scales, it's on the order of billions of years. So this is an example of a major merger, and this is a simulation result of two galaxies of equal mass. And so if they start out at some separation, then once they come into contact here, and then they'll basically emerge, slingshot past each other, come back again, and finally coalesce. And you can see that it's in this case it's about 2 billion years between really coming into contact and finally being a stable galaxy. And so we have names for these. So before you've merged is obviously a pre-merger. So this is technically not the merger itself at all. This part is the first pass, when they first collided and are going past each other. These two things will separate apart like we saw in the movie. You have maximum separation, and then they're going to come back and collide again into the merger phase. And then finally you have post-merger, where things are kind of settling down. There's still some disturbances out here. Stars not really orbiting in a nice way. And then the remnant, which is just a stable, probably elliptical galaxy left behind from, in this case, a merger of two spiral galaxies. And other than simulations, we do have observations that support this. Now, because this takes, billions of years, we can't watch the mergers happen, but we can find, because there's so many galaxies out in the universe, we can look out and find galaxies that are kind of in these different stages. So the top panel is looking at these two galaxies in context. So you can see all the other surrounding galaxies, and that's a nearby star probably. And then in the bottom panel, what you're looking at is for the galaxy pair in each example, you are just zoomed in. So the lower panel is the white box in the upper panel. And again, these four groupings are all obviously different galaxies. We can't watch them merge. So we zoom in here. These two things, this is the first pass, right? These two galaxies are just now about to, or you might even call this is really kind of the pre-merger, I guess. They're just about to merge. This is the first pass. These two have just gone past each other. And then here you're looking at, the actual end of the merger. So it's not the remnant yet. It's really kind of the post-merger. And then finally the remnant. And it's obviously not completely settled. Otherwise, we wouldn't know two galaxies have collided here. But in any case, you can tell this sort of mimics what we see in the simulations. So that makes sense. And just to conclude, one thing you're going to find about mergers probably on the internet, even in the textbook, is this assertion that mergers trigger star formation. So the idea is that star formation is often triggered when gas in a galaxy is sort of forced to become overdense. So you can imagine if you collide two galaxies together, there's going to be, that's going to increase the density of gas in some regions just because you're kind of smashing these two things together. And the idea goes that, well, if you increase the density, that should increase the star formation rate because you're going to be able to have little gas clouds collapse to form stars. And that has been thought to be the case as recently as when the textbook was written, so even up until a few years ago. However, it seems that there's not really any evidence for that. So we can look at a count. This is just basically a histogram of the number of galaxies with a given star formation rate. So you're more or less looking at a count in the vertical axis, and then the star formation rate in a log scale is the horizontal axis. And it doesn't matter the details here, but what you can see is the galaxies that have not had any mergers are in the blue, and the galaxies that have had mergers are in the red distribution, and there's no statistically significant difference between these. The old story goes that the mergers would have had a higher star formation rate. They'd be, you'd have an extra concentration over here. You maybe have a little bit extra, but this is not statistically significant according to the authors of this study. And so, astronomy is an evolving field, and it seems like, galaxy formation, or mergers rather, actually does not trigger star formation is our current evidence. And that is it for this introduction to galaxy mergers for Astronomy 1000.